Hi, welcome to Mrs. Thompson's classroom. Today we're going to be talking about the rational root theorem. The rational root theorem helps us find the possible rational roots of a polynomial, and then we can use our synthetic division in order to find which ones work. We're also going to talk about Descartes' rule, which will allow us to eliminate some of our possibilities and limit our list. So here, let's get started just by talking about what the roots of a function are. So first of all, the root of a function is where the function f of c equals 0. And so we call this a root. And if c is a real number, then it is a real root, okay, also called a 0. That also means the graph is going to intercept the x-axis at x equals c, and that x minus c is a factor of the polynomial. Okay, so what kind of numbers can we get? Well, we can get positive numbers, negative numbers, we can get rational numbers, we can even get irrational numbers. So the square root of 2 can be a root, but we can also get imaginary numbers. So we need to keep that in mind, and we need to think about how that affects the graph. So an imaginary number will not be one of these real roots, of course, but it does affect the function. Okay, so the rational root theorem takes a polynomial. So these a values are the coefficients. We're going to let them be integers, so we're not going to be dealing with fractional coefficients, although we can deal with that. But the rational root theorem tells us that the rational roots of p of x, which are the solutions of p of x equals 0, are of the form p over q. That makes them rational. Rational means a fraction. We're going to put that in lowest form. Now, there are some requirements. The numerator, p, must be a factor of the constant term, okay? And the q, the denominator, must be a factor of the leading coefficient, okay? So let's take a look and see if we can list all of these factors. So p has to be a factor of 12. Okay, that's my constant term. So that would be 1 and 12, 2 and 6, or 3 and 4. Okay, then q has to be a factor of 2. That's the leading coefficient. So those are just 1 and 2. So then we take and we form the fraction of all these values. And it is an integer factor, so we're going to put plus and minus as our possibilities. So we're going to put all of the p values over 1. So that would just be 1 over 1, 2 over 1, 3, 4, 6, and 12. And then we can put them all over 2. So I'll have 1/2. 2 over 2 is just 1, so that's already in the list. Then I'll have 3/2, and then I'll have 4/2. Well, that's 2, which is already in the list. And then we'll have 6/2, which is 3, and then 12/2, which is 6. So these last ones are already in the list up here. Okay, so this is my list of possible roots. I can get rid of those duplicated ones. And this is my list of possible rational roots. Okay, there are no others that can be found to work. Okay, let's do that one more time. So we've got my leading coefficient will find me q equals 1 and 3. My constant term gets me p, which can be 1 and 36, 2 and 18, 3 and 12, 4 and 9, and then 6 times 6. So to find the rational roots, it'll be plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36. And then, of course, I can put them all over 3. So 1/3, 2/3, 3/3 is 1, 4/3, 6/3 is 2, 9/3 is 3, 12/3 is 4, 18/3 is 6, and 36/3 is 12. So they're all listed. So these are my possible roots. Okay. Now, if we want to figure out which one works, we're going to set up synthetic division, and we're going to remember what our remainder theorem told us, and that is that the remainder will equal the value of f of c. So in order to be a factor, I need this remainder to be 0. Now, this is a lengthy list, but I'm just going to pick one. So let's start with a 1. And I do my synthetic division. Oops, 22. So we're multiplying, and then we're adding. And we can see that we get a number that is not 0. So this one does not work. Okay? So we're going to continue this process until we find the one that works. Okay? So we'll erase this. And we will pick another one. Okay? Okay, so let's pick another value. Let's just try 2 this time. So I multiply by 3, and I add, and I multiply, gets me 50, and I add, and I multiply. That's going to give me 142. And then when I add those, I'm going to get 75, which gives me 150. Adding those gives me 18, and 2 times 18 gives me 36, which gives me a remainder of 0. So x equals 2 works. Okay? So then I'm going to keep going down the list. Well, let's try -2. Okay, so I bring down to 3, and I multiply, and I add, and I multiply, and I add, and I keep this process up. And again, I get 0, so it works. So x equals -2 works. But I started with an x to the 5th. So this made an x to the 4th. So now this makes x cubed. So I'm not done yet. So let's keep going. Let's try -3. So -3 times 3 is 9. Add, be -9. Add those, I get 10. Multiply and add and multiply. And look at that, it works again. I get 0. So now I am down to an x squared. So now I have a quadratic. And so I can just solve using the quadratic formula. So -10 plus or minus the square root of 100 minus 4 times 3 times 3, all over 2 times 3. So I get -10 plus or minus. This is the square root of 64. And so when I finish that off, I have -10 plus or minus 8 over 6. And so I get -2/6 and -3. So I can add -3 to the list here, and it occurred twice. And then a -1/3. So this is all of the roots that work. And how many did I find? 1, 2, 3 because of the multiplicity, 4 and 5, and it's a 5th degree, so I found 5 and I'm done. Okay, now some people are going to want to just take these PQ values and plug them into f of x and see which ones equal 0. And if you're using a calculator, that calculation may go quicker, but it doesn't allow you to continually reduce the polynomial and get down to that quadratic. So using that method of finding f of my p over q and figuring out if it equals 0 won't ever find the imaginary ones. But using the synthetic division will find you a pair of imaginary ones at the bottom. Okay? All right, so the one thing we do want to remember, the fundamental theorem of algebra tells us that any polynomial degree n has n roots. Okay, so if it's a 5th degree, it will have 5. If it's a 4th degree, it will have 4. If it's a 10th degree, it will have 10. The thing to remember with that is this will include repeats. Okay, so if something has a multiplicity of 3, it's going to count as 3 of these roots. It also includes imaginary or complex roots. Okay, so if we have a graph, the graph of the function, we may not see all of these roots as actual intercepts on the graph. Okay, so let's take a look at that. So this first one has degree 5, so there are 5 roots. This one is a degree of 4. Make sure you grab that largest exponent, so it has 4 roots. And this one will have 50, because that is its degree. But let's look at the graphs of each of these functions. So the x to the 5th, this is the x to the 5th, this is f1, actually only has 1 root that's visible. So either that root is occurring 5 times, or it's occurring once with 2 different pairs of complex roots. So we would have to sort of figure that out. If I look at the x, this is the x to the 4th, so this is our second one. It has 1, 2, 3, 4 roots. And so it has exactly the amount that we thought it would. Okay. But then finally, if we look at f of the third one, whoops. If we look at that third function, it doesn't have 50 roots. In fact, here's my axis down here. It doesn't cross the axis at all, so it actually has no real roots. But it's got 50 complex ones that may be repeating themselves. Okay? All right. Now, that list of possible roots can get lengthy. So Descartes' rule of sign is going to help us limit down the possibilities. So Descartes' rule of sign says that if f is a polynomial with real coefficients, then the number of positive real roots is either the number of sign changes in f, or the number of sign changes minus a multiple of 2. Okay? The number of negative real roots is either the number of sign changes in f of negative x, or the number of sign changes in f of negative x minus a multiple of 2. Now, what do we mean by sign changes? Okay? Well, basically, when you take a function, let's just look at one. This is positive, positive, negative, positive, positive. So I have one sign change here, and I have another one here. So this one would have 2 sign changes. So it has 2 positive real roots or none. Okay, so let's take a look at an example here. How many positive and negative roots are possible? Well, if we look here, I have a sign change here, and I have a sign change here, and I have one here. So that makes the positive one are either 3 or 3 minus 2, so that would be 1. So I either have 3 positive roots or I only have 1 positive root, but I won't have 2 of them, and I won't have 4 of them, I'm only going to have either 3 of them or 1 of them. Now to get the negative roots, I need to find f of negative x. So that means I'm going to put a negative x into the equation. Now when we do this, anytime the exponent is odd, it's going to keep the negative sign. But anytime the exponent is even, it will become positive. Okay, so this minus a negative will become a plus. So now I go from negative to positive. And here at the end, I go from positive to negative. So the negative real roots are either 2 of them, or 2 minus 2 would be 0. Okay, so if there's 0 negative roots, I'm probably going to have 3 positive ones, which might leave me with 2 imaginary to get to 5. Or I could have 2 negative and 3 positive, and then that's 5, and they're all real. Okay, but this does help me limit down the number of possibilities. So let's do this again. So here I have 1, 2, 3 sign changes. So my positive roots are 3 or 1. F of negative x will be negative x cubed minus 9x squared minus 26x minus 24. So all the odd exponents will change signs. The even exponents will keep the sign. So if I look at this, everything's negative. So the negative roots, there are none. Okay? So this is helpful because now when I go to actually find my roots, I know that I don't have any negatives. So when I look at that P over Q, I don't have to even try the negative results. Okay, so let's do my P over Q and actually find them. So the P has to be a multiple of 24. So the P is going to be 1, 2, let's see, that would be 24 or 12, 3 and 8, and 4 and 6. And Q is 1, so all of these over 1. And then it would be plus or minus, but I know I only have to deal with the positive ones. So now I just start trying them. So I put my coefficients. And I pick one. So let's look at, let's just start with, let's do positive 1 first. So I'm putting down my 1 and I multiply, I add, and I multiply, and I add, and I multiply, and that one doesn't work. Okay, so I go and I erase this. Okay, and I'm going to try another one. So maybe we try 2. Two times 12 is 24, and that one works. Okay, now I started out with an x cubed, so as soon as I found 1, I now have x squared minus 7x plus 12. This actually factors to x minus 3 and x minus 4. So my answers are 2, 3, and 4. So it was a 3rd degree. So it had 3 roots, and they were all positive, 2, 3, and 4. Okay. All right, so hopefully that helps. Next video, we'll get into dealing with polynomials when they have those complex roots, and we'll even look at some that have irrational roots and how to deal with those. But hopefully this gets you started, and we will see you next time. Thanks for joining me.